Source followers. Source followers are occasionally employed as level shifters or buffers, impacting the overall frequency response. Consider the circuit depicted in Figure A, where CL represents the total capacitance seen at the output node to ground, including CSB1. The strong interaction between nodes X and Y through CGS in Figure A makes it difficult to associate a pole with each node in a source follower, neglecting body effect for simplicity and using the equivalent circuit shown in Figure B. We can simply sum the currents at the output node. V1 CGSS plus GMV1 is equals to Vout CLS. Obtaining V1 equal to CLS by GM plus CGS Vout. Also, beginning from Vin, we can add up all the voltages Vin equal to RS V1 CGSS plus V1 plus Cout CB CGDS plus V1 plus Vout. Substituting for V1 from equation, we have Vout by Vin S is equals to GM plus CGS by RS CGS CL plus CGS CD plus CGD CL into S square plus GM RS CGD plus CL plus CGSS plus GM. Interestingly, the transfer function contains a zero in the left half plane. This is because the signal conducted by CGS at high frequency acts with the same polarity to the signal produced by the intrinsic transistor. Figure A, source follower, B, high frequency equivalent circuit. If the two poles of equation are assumed far apart, then the more significant one has a magnitude of omega p1 is equal to GM RSC GD plus CL plus CGS is equal to 1 by RS GD plus CL plus CGS by GM. Also if RS is equal to 0, then omega P1 is equal to GM by CL plus CGS. Let us now calculate the input impedance of the circuit. Nothing that CGD simply shunts the input and can be ignored initially. From the equivalent shown in figure, the small signal gate source voltage of M1 is equals to Ix CGSS, giving a source current of GM Ix CGSS. Starting from input and adding the voltages, we have Vx equal to Ix by CGSS plus Ix plus GMIX by CGSS into 1 by GMB parallel to 1 by CLS. Figure calculation of source follower input impedance. That is Zn is equals to 1 by CGSS plus 1 plus GM by CGSS into 1 by GMB plus CLS. At relatively low frequency, GMB is greater than mod CLS and Zin is similar to 1 by CGSS into 1 plus GM by GMB plus 1 by GMB, indicating that the equivalent input capacitance is equal to CGS GM GM by GM plus GM. This result can also be obtained by Euler approximation, since the frequency gain from the input to the output equals GM by GM plus GMP. The effect of CGS at the input can be expressed as CGS into 1 minus GM by GM plus GMB equal to CGS GMP GM plus GMB. In other words, the overall input capacitance is equals to CGD plus a fraction of CGS. At high frequencies, CGMB is less than mod CLS and Zn similar to CGSS plus C1 by CLS plus GM CGS CLS square. For a given S equal to J omega, the input impedance consists of the series combination of capacitors CGS and CL and a negative resistance equal to minus GM CGS CL omega square. The negative resistance property can be utilized in oscillators. The output impedance of source followers is also of interest in figure A. The body effect and CSB simply yield the importance in parallel with the output. Ignoring this importance can neglect in C. It is noted from the equivalent circuit of figure A that the V1 CGSS plus GMV1 is equals to I minus Ix, also V1 CGSS plus CGSS RS plus V1 is equals to minus Vs. Dividing both sides of this equation gives Z out equal to Vx by Ix equals to Rx GSS plus 1 GM plus HTM plus CGSS. It is instructive to examine the magnitude of this impedance as a function of frequency. At low frequency, Z out similar to 1 by GM as expected. At every high frequency, Z out similar to RS because CGS shorts the gate and the source. Therefore, we summarize that mod Z out varies as in figures B or C, which one of these variations is more realistic operating as buffers. Upper source followers must be lower than the output magnitude, that is 1 by GM less than RS. For this reason, the characteristic shown in figure C occurs more commonly than in the figure B. The behavior illustrated in figure C reveals an important attribute of source followers. Since the output impedance increases with frequency, we postulate that it contains an inductive component. To form this case, the representative Z out by a first order passive network, nothing that Z out equals to 1 by Gm at omega equals 0 and Rs at omega equal to infinity. The network can therefore be assumed as in figure because R1 equals to R2 at omega equals 0 and R1 plus R2 at omega equal to infinity. In other words, Z1 equals Z out if R2 is equal to 1 by Gm, R1 equal to Rs minus 1 by Gm, and L is chosen properly. To calculate L, we can simply obtain an expression for Z1 in terms of the three components in figures and evaluate the results that are found above. Alternatively, since R2 is a series component Z1, we can subtract this value from Z out, thereby obtaining an expression. Figure calculation of source follower input impedance. Figure equivalent output impedance of a source follower. For the parallel combination of R1 and L, Z out minus 1 by Gm is equal to CGSS Rs minus 1 by Gm plus Gm plus CGSS in inverting the result to obtain the admittance of parallel circuit. We have 1 by Z out by 1 by Gm equal to 1 by Rs by 1 by Gm plus 1 by CGSS Gm into Rs by 1 by Gm. We can identify the first term on the right hand side of the inverse of R1 and the second term as the inverse of an impedance equal to CGSS by Gm Rs minus 1 by Gm, that is an inductor with the value L equal to CGS by Gm into Rs minus 1 by Gm. The dependence of L upon Rs implies that if a source follower is driven by a large resistance, then it exhibits substantial inductive behavior. As depicted in figure, this effect manifests itself as ringing in the step response if the circuit drives a large load capacitance. Figure ringing in source of a source follower with heavy capacitive load. Thank you.